once again. Yesterday I was a bit hurried at the end of my lecture, and I didn't get to answer some of the questions I had promised to answer about high dimensionality and what happens with sampling too close to the borders. I've given the slides to Zico, and in those slides there's information about that. But essentially, in short, if there are two ways of attacking high dimensionality now in Bayesian optimization. One's via trees, because in trees, as in random forests, like Zico explained this morning, you choose a dimension where to split. So you essentially are picking the relevant dimensions. And so you can attack problems of up to a couple hundred dimensions, as people have done effectively. Frank Hutter has a system that handles about 300 parameters. And they're able to automate software out there. So in particular, there's a very nice paper called AutoWeka where they tune Weka for you. And in particular, they tune 300 parameters. Many functions in high dimensions are also of the nature of some parameters matter more than others. So sometimes you're tuning and some parameter is very critical and another one is not very critical. So in other words, your cost function is fairly constant along a dimension. If that's the case, you can construct randomized algorithms that allow you to essentially do optimization in a lower dimensional embedding of this high dimensional cost. So even though the cost function is high dimensional, only some parameters matter, and it's possible to use randomized algorithms to discover those dimensions efficiently and be able to search in low dimensions. And if you Google for Bayesian optimization billion dimensions, you'll find that there's a paper that solves Bayesian optimization in a billion dimensions, provided the true dimensionality is small. There's no magic. If the problem is naturally high dimensional, we have no ways of doing it yet. There's a lot of work to be done there in terms of scaling Bayesian optimization to high dimensions, to high numbers of data, and also in terms of robustifying it with respect to the choice of hyperparameters, heteroscedasticity, choices of the boundaries of the decision set where you're going to be searching for hyperparameters and so on. So there's a lot of work to be done there. So if that sort of thing interests you, there's certainly a few PhDs to be written on the topic. All right, so today I'm going to attack a problem that a lot of people have played with, but where it's been much harder to make progress. So where the algorithms are in general not robust, or they don't seem to be robust, and where it's sort of very cool, but in the end, the demos that you'll ever see at the conference are these sort of simple grid worlds, and it's sort of frustrating to get things to work. Zico, by the way, had some of the best RL work that I've seen. Maybe he'll add it to some of his lectures. Okay, let's get into it. A decision problem or an RL problem will have the following elements. First, there will be a state, S. Now, a state for an agent is all its percepts, what it sees, what it feels, the temperature sensing, and so on, as well as all its memories. Like, I have a neuron that is firing right now to indicate that I'm here at this particular location, and that I'm standing at this particular location, and so on. And so those memories, those activations that basically give me my current sort of relation in the world to you guys and to everything I sense and do, that's the state. And so coming up with a good representation for state is extremely hard. And mostly people have been using these sort of grid worlds, and obviously that's where the problem is. One of the fundamental problems of RL is being able to say what the state is. And today, what I'm going to try to get to is a nice application of RL that came out last year by a company called DeepMind, where the thing that I like the best in their demo is their representation of state. And it made me so excited to see this new representation of state that I decided to go back and do research here. Now, an agent interacting with the environment acts. So there will be actions A, and these actions will be from some space A, and the actions are only based on different states. Excuse me. You can choose different actions. So think of a state in the sense as a context. When I'm in a particular context, I'm allowed certain actions and so on. The agent is part of an environment. And I will assume that that environment makes the state change. And in particular, that environment will be stochastic, where I'm going to have a noise variable which could depend on the previous action and state. Okay, so you sense the world, you act upon the world changes. And it changes in a deterministic fashion, but it also has unpredictable elements to it, which I encode with epsilon. The agent has as a goal to find a policy, and you should think of a policy as a strategy. And let's assume that we're going to deal with the agent having to make capital T decisions. In that case, that policy will be a sequence of functions where each of these functions maps the state to an action. Okay, so how I make, which actions I choose based on the state comes from this function mu, and this function mu will change over time. We say that when such policies change over time, we refer to them as, we're going to refer to them as non-stationary policies, as opposed to a stationary policy where the function is the same no matter what time you're deciding. In this case, the decision problem goes up to t steps into the future, and so this is called a finite horizon problem, with the horizon here in particular being capital T. I will use this MATLAB notation or Python notation, whatever you want to call it these days. It's very common, and so pi naught to t refers to pi naught, pi 1, and so on. Okay, so that's the setup. I don't know if I've been optimal in this choice. Let's see. Okay, that's good. So in addition, so the goal is to find a policy, and you find a policy to maximize the expected returns. Or value. I'm going to define that to be this function v pi and I will assume that I'm starting at a random variable s naught equal s naught. So this is the value of the variable, and that's going to be an expectation over w, sorry, I'm calling it epsilon. Epsilon naught to t a sum from t equals 0 to capital T of R Okay, let me parse this equation. What I'm going to do is try to maximize a sum of rewards. So these R's will stand for rewards. And they're the immediate rewards. They're the reward that I get from when in state S, choosing an action according to the policy mu t. And that reward has a stochastic element, which is captured by this epsilon. So there's a cost, there's some objective that I'm trying to optimize, but that objective has some noise to it. So pretty much in machine learning, all problems are of this nature. We're always trying to find the parameters for a certain amount of data that we've seen, but we haven't seen all the data in the universe. So we've seen a finite set of the data. So all our problems are stochastic because of our limited observability of the environment. This expectation is over all the possible uncertainty in the future. So the way to interpret this is it's an expectation with respect to this, the distribution of the environment. In particular, how I go, so it's over P of E naught or P of E1 given A naught and S naught dot 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 P of ET given AT and ST. Okay, so the expectation is over this sort of every noise variable in the system. We will define the optimal value function starting at state S naught to be the max over this policy of V pi of S naught. So it's basically the value function when you've chosen the best policy over all time steps. Okay, the first way to solve this is something called model-based RL. And so in model-based, we will assume that we know the distribution of that noise. So we know how the world transitions, how the noise depends on AT and ST. We will have essentially someone will give us a simulator. And so we know the function, we know this distribution, and we know the function f. And so, for example, in environmental problems, people have spent a lot of time describing how a particular ecosystem might evolve over time, how the trees die and the squirrels come in, et cetera, et cetera. So you have these very complex simulation models. So if you want to come up with a policy of how you're going to interact with the environment to harvest resources, then you might as well use one of those simulators and then try to find the best policy to harvest the environment in a sustainable way. In such cases, we might also want to parameterize the policy. So the policy mu will have some parameters. So you might have that each action will be a function of a policy that has some parameters theta. And so your goal is to come up with the best parameters for this policy. And in particular, it might be often the typical case is that this policy is stationary. So the policy, so I'm deleted the t there to indicate that it's the same function no matter what time you are. So what you want to do is just come up with a function that will look at the environment and will tell you what you should do. So one way to do this is to simulate. And when we do simulation, what we're going to do is we're going to sample E naught to t from the probability. I'm just going to write it for short like this. But by that, I mean that probability. So you sample E naught first, the system transitions, then you sample E1, the system transitions, you have to compute F, and then you sample E2 and so on. And often it's good to decouple the noise from the deterministic component of the system. That's always a sensible thing to do when building algorithms. Because if you do that, the noise becomes independent. You can, and you don't have to simulate from these very highly correlated distributions. A lot of the techniques that I used in deep learning, in fact, things like if you've heard of dropout, for example, they do that. They try to decouple stochasticity from the deterministic component. Now, assuming that we have drawn several samples of this, and I'm going to use an I to indicate samples, and these I will be from 1 to n. So I've drawn n samples from it. Now I can approximate my value function. Oh, and I should say, using I'm drawing samples from this. But essentially, the way I draw samples from this is I pick an E, I draw an initial sample, and then I need to choose, using this policy, I choose the next action. So I draw a sample I. And then my state also comes from using the function f. So given the function f, I can move to the next state. I start with some initial state, and then I move to the next state with the function f. I move to the next A with A, and then that way I'm generating all the basically all the rollouts of A's and S's. Probably I should draw the graph here. So if you want to think of it in the type of graph I have is one where I'm transitioning like this, where I have a state variable, transitions to another state variable. I have a deterministic policy parameterized by a parameter theta that gives me the action. And then the new state is a function through the function f, and through the probability distribution p, I generate the next state. And then I have a reward, which is a function of these elements here, of 3 stages, because this basically encodes epsilon, A, and S. This is called an influence diagram. Usually we use round circles to indicate random variables, boxes to indicate actions, and then diamonds to indicate rewards. In my construction, I'm making the reward be a function of S, mu, and epsilon. Often, the reward is just a function of S and mu as well. So, and you could derive everything just by doing it that way. That's not terribly important. I've just picked these notations, and I'm going to stick to that. So this is using mu. So in particular, for a particular theta, I can generate all these guys. And once I have the epsilons, because I know f and I know pi, I know every s and I know every a. So I can do the rollouts. And so then I can approximate phi pi of s naught, and I'm going to put a hat to indicate that it's an approximation, using Monte Carlo samples. And I'm going to sort of emphasize that this is as a function of that parameter theta that I've chosen. And so that will involve these rewards of all my future S's using my parametrized policy. And of course, the noise sample. Okay? So since I can simulate the future, I can simulate the future rewards, and I can just take a Monte Carlo average to get me the value function. Now, my goal is to optimize, to maximize this over theta. And let's assume that I have 10 thetas, and I want to maximize this function. What algorithm would you guys suggest I use? Pardon? Thank you, Bayesian optimization. So you can also do gradients here, but it's actually kind of tricky and they're sort of somewhat unstable. This is a very noisy function. So Bayesian optimization is not only good when you're doing black box and you don't have expressions for derivatives, although if you do have expression for derivatives, you can define a GP over both the function and derivative, and you can do a bit better if you have that information. But it's particularly good because this is expensive. Doing simulations into the future is very expensive. And also, it's noisy. And so when you do finite differences to try to approximate gradients and so on, you often, and even if you try to do it exactly, when there's noise in gradients sometimes can cause instability. So it's one of those cases where if you have just a few parameters, doing exploitation exploration with Bayesian optimization gives you a very easy way of optimizing that. And I will show you some examples where we do use policies that are basically neural networks, and we optimize these functions. Okay, so that's all of it. And I'm thinking that I kind of would like to keep these definitions here and use that board. I will need help from the organizers to shift the board up. I'm going to erase in the back here. I'm sure this looks funny. All right, so that's model-based. Next, I'm going to do the model-free light. Lighting. Oh, okay. All right, thank you. All right, where are we? So we've defined the value function. We've described how to do model-based RL. And now we're going to do, so this requires that you have a model. A lot of problems you don't have a model, but you're acting on the world, you're learning a model as you go. So you're learning a model and you're making decisions at the same time. So we're going to look at another way of doing this called model-free RL. And the free is because I actually believe that you actually do end up building models as you go. The value function is a model. So we're going to, for model-free RL, we're going to derive one of sort of the most fundamental things in reinforcement learning, which is dynamic programming / Bellman updates. or Bellman optimality. Now, let's assume that we have a value function and that we are at the decision stage t. And in particular, let's assume that I have the optimal value function at time t. So start for the optimal. And so we know that that's the max of pi t to capital T of the expectation over all the noise variables, also from stage t to the end, of the reward function. Let's just use the variable k, from k equal t to capital T, and then this would be RT of st pi, mu t of st, and I'm missing et. Okay. Instead of writing this all the time, I'm just going to call this whole thing RT in the next few steps. That value function can be distributed. Oh, I missed. So you need to close the square bracket. I think I forgot one bracket up there. That value function, what we're going to do next is we're going to distribute the expectations and the max operators. So we're going to try to take as many inside as possible. So basically, what I'm going to do is this. Right now I have something that's written in this form, and I'm going to change it to something that looks like this. So I compute b plus c, I store it, and then I multiply it times a. Dynamic programming, basically. Much of machine learning is about just multiplying numbers that way. Belief propagation and so on are just examples of it. So let's assume that we start by distributing the expectation. So I'm going to write this as the expectation with respect to ET. And then I'm going to break that reward into two rewards, RT, and then a sum from k equal t plus 1 to t of rk. And I've moved an expectation inside. And this was the expectation from, run out of space, t plus 1 to t. Actually, let me rewrite that so that it's clear. T plus 1 to t, sum over k equal t plus 1 to t of rk. And do stop me if I make any mistakes or if anything is not clear in terms of notation. Go ahead. Oh, pi. Thank you. Still maximizing over the policy. And now I've brought back the fact that it's non-stationary. I'm going to do the more general case, and then if it was stationary, each pi t is just the same mu. Okay. And so currently, the pi that I'm using is as denoted here. Is the sequence of functions. So I'm maximizing finding the best function. So in other words, t plus 1 functions. And I'm taking the expectation over all the uncertainty. So I'm marginalizing, getting rid of all the noise in the system. And here, because RT is not a function of t plus 1, I can take it out of the integral. So I've just distributed it. The other thing I can do now is distribute to the max. And so this now is mu t. And the reason why I will be able to distribute the max is because this does not depend on this doesn't depend on pi t plus 1, anything that happens after time t in terms of the policy, so it's just a constant function. And this term here, the reward at time k, as you can see in that expression, will only depend on the first epsilon, which is epsilon t plus 1, so it doesn't depend on epsilon t. So I can now rewrite this as RT plus the max over pi t plus 1 to capital T of the expectation of epsilon t plus 1 to T of the reward function. Or in other words, this is equal to the max over mu t of the expectation of the current noise of my immediate reward. And if we look at the expression there, this is nothing but the value function again. And voila, we've derived one of the most important equations in RL. So that's the value function. And that basically essentially prescribes how we can do updates. So if you have a representation of a function, we haven't talked about representation yet. I'm just calling it a function, but you're going to have to code it somehow in a machine. So if we have a function, and we want to learn a function, this sort of prescribes an algorithm for doing that, because essentially we start with a function, we compute this, and we get a new estimate of the function. So we could iterate this fixed point and hope that things will work out, that we will get a valid estimate. And indeed, you do, and there's many convergence results about, you can show that this is a contraction operator, and you can show that this actually stabilizes, and you're able to estimate the value function. Now, there are also infinite versions or infinite horizon versions of this equation. And the infinite horizon is just exactly the same thing. But in the infinite horizon, what we have is the objective is a sum from t equals 0 to infinite of RT. So we try to find the expected rewards, even if those rewards went to infinity. And so what we then do is we introduce this thing here called the discount factor. And a discount factor, essentially, what it does is it's, because we're exponentiating it to a power, it's going down to 0. And it just makes sure that immediate rewards, early rewards, are more important than future rewards. Now, choosing this turns out to be an extremely hard problem. And in practice, what you would want to do is marginalize this. And there are algorithms that try to integrate out this, put a prior on this, because it's essentially like a geometric prior. And that gives rise to something called TD lambda and so on. I'm not going to go into it, but it's being able to decide, like to give you sort of an example of why this is important. Imagine you're playing chess, and all of a sudden you win. And you have to figure out what all the actions that you took in the past were the decisive actions that made you win. So in a sense, there is a delayed, the rewards tend to often be very delayed. So the rewards are very uninformative, and all of a sudden, boom, your reward becomes very informative. And you're not quite sure which of all the actions were the ones that sort of mattered the most. So that's called the credit assignment problem. And it's one of the hardest problems to solve. Definitely worth a few PhDs if you can figure it out. Okay, so in the infinite horizon, we often try to maximize the sort of expected sum of future rewards, discounted rewards. And in that case, the value function of a state can be written as the expectation, just the same as what we have there over epsilon t. Whoops, I forgot the max. And let's say that I just have a stationary policy, so it's the max over mu. Or if it's stationary, I can just put an a, because a is just equal to mu of x. So I'm just going to put straight a. And it's the same as that. So you have RT. And again, to emphasize that RT, in fact, I'm going to drop the t's. And I'm just, because there's a back, so there's time t and time t plus 1, I can just introduce some symbols. Right, sorry about that. I'm just going to rewrite this as SA moving to state S prime. And then there's going to be a discount factor, gamma V of S prime. That's a sort of formulation that you often find in books. So the only new thing here, I mean, I could have just called this epsilon and allowed for the function f, and then the notation would be exactly the same. But I'm trying to bridge it to the notation that you might see more often in the machine learning literature. The other new element here is this discount factor. But the same derivation that I just did, distributing the sums and the maxes, you could just put this gamma there, and you'll see that as an exercise, it's really trivial to get this other form of the equation. Okay, so often when you have a control problem, let me rewrite this again as a function, pi of s, just to illustrate the following. Let's assume that I want to solve this for a discrete problem. So my least favorite example, where you have a guy acting in the world, and I guess he has to move in this grid world and find a place where there is pounds, which I think is the currency that's doing well these days. And so he basically has to do this, so get a PhD and so on. Now, you can map this. So this is a discrete state space. So you might want to basically find out what's the value of being in each cell, with this value of being here being higher than, say, the value of being here. And so in this case, this value function will look at all the discrete states, and there'll be one value for every possible discrete state. So this will be a vector, essentially. So you're going to have a vector that depends on v pi. This reward will be a vector as a function of pi. And we're going to have this reward once you've taken the integral, once you've taken the expectation. And then we have a transition matrix because associated with S prime, so the idea is I'm rewriting this now as P of S prime given A and S, as opposed to rewriting it as P of epsilon given A and S. So in the discrete state spaces, it's more convenient to just write it as a transition table. So for a particular, or in particular for a, what this is a function that takes as input S and outputs S prime. So I can write it as a matrix from S to S prime times a V function. And so when you actually implement these algorithms, all you're doing is you're solving a linear system. And so the computation, it will, depending on how you solve it, will be n cubed or n cubed times, or n squared times the number of iterations. And all these different ways of solving this leads to different algorithms out there, like value iteration, policy iteration. They're just ways of solving linear systems. Sometimes you take into account the structure, block diagonal structure of these problems, and you can even do standard machine learning techniques like belief propagation with EM algorithms, because this is sort of an expectation maximization problem, and you can actually solve for this. But I'm not terribly interested in that stuff, because those discrete state spaces, they're interesting in operation research. They will not give us anything remotely closely to what we aspire with AI. Okay, so I'm going to leave that equation there. And I'm going to switch to this board. And we're going to introduce the first algorithm for doing this, which is called TD0. And it's a stochastic approximation. In order to do stochastic approximation, I'm going to go back to this equation, either this one or that one, it doesn't matter. Let's pick the infinite horizon one. And I have an expectation here. And so I'm actually first going to write, I'm going to remove the maximization step, and I'm going to make this a function of the policy. So this is going to be V pi expectation of S prime over S prime. That is expectation over the probability of S prime given S. R of A comma S comma S prime. And actually I'm going to write here, pi of S plus the discount factor times the future value function. Okay, so I've just rewritten this. I've taken away the max operator, so now I'm just making it as a function of pi. And that particular expression, again, you can go back and you can quickly convince yourselves that by distributing sums, you would get this. This is a fixed point. I have V pi on the side and a V pi on the side. So it's like when you solve a linear system using Gauss-Seidel or the Jacobi iteration methods, if you've seen those before. But unfortunately, it has this expectation, which can be intractable for most problems, because in discrete state spaces, this will typically be an exponentially large expectation. Soon getting you into trouble for all sorts of interesting problems, really, except the silly grid worlds. And even for continuous spaces, this might be a non-standard distribution, maybe products of t's and gammas and so on, which make it very hard to, or you might want to have a neural network here, which has some sort of interesting representation for the transition of the environment. So doing that expectation by hand is very hard. So I think for all intents and purposes and practices, it will always be intractable. So what we can do is we can approximate it. Now, what I'm going to show you next is my recipe for my personal way of how I derive algorithms in this setting. So I basically, the way I go about this is I multiply both sides by alpha, and then I add v pi to both sides. Okay. Now I'm going to rewrite. I'm going to move this guy to the right, and I'm going to write v of s pi is going to be equal to v pi of s plus alpha times, I'm going to just write RT, plus gamma v pi of s prime. And then I have minus alpha. Oh, oops, the alpha is a common factor. And I have minus v of s here. And I'm missing an expectation. I'm missing an expectation here. Which should have been this expectation. Oops. Okay. So I have that expectation, and I've moved this here. So the next thing that I'm going to do is the following. I'm going to draw, I could draw more samples, but I'm just going to draw one single sample from the distribution of S prime. So I'm going to draw S tilde from P of S prime given S comma pi of S. And I'm going to approximate then this with V pi of S plus alpha times RT plus gamma V pi of S tilde minus V of S. All right, so I've drawn a single sample from the distribution to approximate this way. I could have drawn more samples, and then I would have done what I did when I did simulation, 1 over n, sum from 1 to n. But it turns out that to get convergence, you only need one sample. So it's the same as when you do stochastic maximum likelihood, or for those of you who've seen deep learning, when you do try to train a Boltzmann machine or a log linear model, a CRF and so on. And that's it. That's the algorithm. So the only thing you need to do now is, so this is the old value function. This essentially is the new value function. So we can put an index over this. I don't know, over I plus 1. You have a discount factor here. And then this is I. So this is the old function. And I have some representation for this function. I haven't told you what it is. So if this is a neural network, this will be the parameters of the neural network in the previous iteration, and that will give me the new neural network with the new parameters. So to make this a bit more clear, it might be actually useful to look at this in terms of something we've seen before. Something that Zico introduced us to. So in particular, if we have a loss function that we're trying to minimize, so you have some loss function of parameters and data with respect to some distribution that the environment that is producing data that we need to minimize. That's the classical scheme for minimizing a loss in machine learning. The data comes from here. So in particular, if you have data samples, we can, from the distribution of the data, then the problem takes the form minimize of a theta 1 over n, sum from I equal 1 to n, the loss function of theta with values xi. Okay, so that's what we do in machine learning. We don't know the expected loss, so instead we minimize this empirical loss. Now, let's rewrite this as min of a theta expectation of the loss of theta and x. What I'm going to do, I'm going to assume some regularity conditions, and I'm going to argue that then the fixed point for this is grad loss of theta comma x p of x dx equal 0. And now I'm going to do exactly what I did in order to derive the TD0 algorithm. I multiply both sides by alpha. In this case, I'm in the parametric world, so instead of adding the function, I'm going to add parameters on both sides. And I'm going to draw samples from P of x. And I have my algorithm. Theta at iteration t plus 1 is going to be equal to theta at iteration t. Oops. I need new chalk. And let's say that I move this to the other side, whichever is minimization, minus alpha. And then I'm going to draw, say, n samples. And let's say from n equal 1 to n, grad L of theta t, comma, I think I drew the line too close to the edge. Let's write it this way. So that would be gradient descent, stochastic gradient descent. And it's stochastic because you haven't seen all the data. That's the only reason why we call it stochastic. And again, in stochastic gradient descent, we only need one sample. So we can just write it this way. Okay, and that's the version that we saw before. So the way to derive all these stochastic approximation algorithms is essentially the same. And that's our gradient, our friendly gradient descent algorithm to minimize losses. Now, why does this make sense? Let's do the following. Let's make this equal to theta t minus alpha grad L theta t comma xt. And I'm going to add to this alpha times the expectation of the gradient of L minus alpha, the expectation of the gradient. So the expectation of the gradient being this expression here. So the true gradient. And so I can rewrite this as theta t minus alpha, the expectation of grad L, plus alpha times this difference. The true gradient, that is the gradient if I knew all the data of the universe, minus the gradient when I only know one single data point. Okay, and I'll close that bracket. So this is basically saying the stochastic gradient descent, this equation, is just gradient descent. Like if you ignore this term, that would give you the full gradient descent. But now we have this noise term. And this noise term is the discrepancy between the true gradient and the gradient at the current time step. Okay, so, and this is why this is stochastic, because it's the not knowing the true gradient and only having the gradient at time t. Now, this immediately, when you write it, I prefer it in this form than in this form. If you want to do theory, this is a nicer form, because when you look at this expression, you already see that what has to happen asymptotically is that this has to disappear. This term has to stop mattering, because you want to do descent in the true gradient eventually asymptotically. So in a sense, to make this vanish, it's nice to decrease. The first temptation might be, let's make alpha go down. And so folks often choose this to be 1 over t. Why does 1 over t make sense intuitively? Has anyone thought about it? What's the sum of 1 over t? Or sum over t of 1 over t, of the sequence 1 over t to infinity? Pardon? No, yes, I heard the word divergence. So maybe forget t, imagine it's an n. Sum of 1 over n, we've did this in calculus, diverges. Now, why is it a good thing that it diverges? Because you kind of need that because you need to go from the initial theta to any possible theta in the space. So if you're optimizing over the entire space, if this guy went to 0 too quickly, you might not visit the entire space. On the other hand, the sum over 1 over t squared, i.e. the variance of this, is bounded. And so essentially the reason why you choose 1 over t is when we do the analysis, we want to bound the variance of this noise. Bounding variances gives us bounds on probabilities and we get convergence. However, if your space is compact, if you know the size of the box over which you're going to optimize, you don't need to visit the whole space. So in that case, there is actually an optimal eta alpha that is constant. Moreover, and there's some very good work by Nemirovsky and Shapiro and colleagues showing that. Moreover, a good trick to do when you do this type of optimization, and it's true in RL, is to do something called Polyak averaging. So what you do there is you choose a fixed learning rate, sometimes a large learning rate. And so what happens then, let's do it with a picture here. If you go down the cost function, even if it's a convex function, it's a good, especially if it's a convex function, it's a good idea to do this, is to take big steps and oscillate. And then what you do at the end is you take the average, and boom, you get the optimum. As simple as that sounds, that is one of the most effective techniques for stochastic gradient descent or stochastic optimization algorithms. Polyak averaging. Take big steps and average. And essentially, you can show, and Francis Bach has a beautiful paper on this, that what you're doing is you're following a Markov chain when you have a fixed learning rate. And when you're averaging, what you're doing is you're computing an ergodic average. And he does some very nice analysis for this in the case of convex functions. So it's Francis Bach and Eric Moline. A beautiful, I think, 40-page math paper that is worth reading if you ever find the time and the love. Okay, so that's basically it. Now I want to just conclude with one last thing here that we're missing. which is Q functions. And I think for Q functions, I want to use this. And I will soon run out of time, so I'm going to just state the main result. And it's 3 lines to the right, but you can also define, just like I did for S, I could have defined a function over S and A, assuming that I start at state S and I start at action A. And that likewise would have been the expectation over S prime over R plus gamma. And then I would have been able to distribute this action inside. Okay. So if I define the function instead of being in terms of Vs, in terms of S comma A, then I can derive this particular recurrence following essentially the same type of work. This is called the Q function, or the Q factor, or the action value function. And if I apply the same trick that I did before, I multiply both sides by alpha, I add Q to both sides, I rearrange terms, I get an algorithm called Q learning. And Q learning is just the same thing as these methods. So I wanted now to just give you an example of this. And how do I think? And then we can break for lunch. So in particular now, I'd like to show you a little bit of what DeepMind did, which is actually an application of Q learning where the Q function is a deep net. That's basically it. And so we're going to update the parameters of that function. Pardon?
Doesn't let you turn on the lights when it's
Oh, okay. And this guy in 6.5. Okay. So let's see an example of Q learning in practice. So now it got kind of dark, but it's okay. So what this company, DeepMind, did, what I really like, is they decided to create a reinforcement learning agent that basically just looks at the screen of the game, and then it learns to choose a set of actions to play the game. So just like a human faces a screen and plays with a joystick to win a game, this machine learns to play Atari games. So you have an environment, in this case the Atari simulator. You have a set of discrete actions. What's really interesting is the representation of state. You have images X, and then the state is a sequence of images and the actions. So you're storing in your head a trajectory. And I really like that because of the following. Can you say the alphabet forward quickly? Now say it quickly backward. No. Okay, we store sequences, and we don't do random access. Same as your phone number. You can say it very quickly forward. It's really hard to say it backward. It's a good test to see if you're drunk. Try it at a party. And they also use discounted rewards. And sequences are really important. One of the founders of this company actually has a very nice paper where he shows, actually just very quickly, let me take you back here for a bit. So one thing so Quark will tell you all about these deep nets that learn local edge detectors in the visual cortex, and eventually as you go higher up, they learn cork faces and cat faces and so on. So that's sort of compositionally making images out of small elements. But there is also neurons that are very interesting called place cells or grid cells that essentially fire as shown here in this caricature, they fire indicating where a rat is. They're in the hippocampus. It's where we form short-term memories as well. And so in the same place where we're putting these sort of episodes of memory, these episodes of little video that we've seen, it's the same place where we're also composing plans. People that have damage to the hippocampus, they're not only bad at storing immediate memories, so they can't form new memories. Like there's a notable patient, HM, I think, that had that issue and recently passed away. But also, you make plans, it seems, by pasting these memories. That's how you imagine and compose the visual world and your dreams and so on. So sequences in the brain are really important. So I like the state representation for that. Even though, admittedly, this is just an Atari game. So we're still in the 80s here, although these were pretty good. And then the Q function is, as I just defined, maximize over some policy the expectation of all future rewards. Now, that's the equation that I wrote now on the board for the Q function on top. But in this case, instead of having the true function, what we're going to do is approximate the true function with a neural network, like Kwok will teach us this afternoon. And so that neural network, the Q function, will now have parameters theta. And I'm going to assume that the Bellman backup, for some data, A prime and S prime, that I will soon say where it comes from, is the observation. Why? And I'm going to try to fit the neural network to the Bellman backup. And that basically, if you take derivative, again, gradient descent on this, it takes this form. This is the very classic reinforcement learning with neural networks work, which is very old, but was never done well. So now where does the data come from? The idea is you're going to create a database where you're going to store states, which are sequences of actions and images, the rewards, and the sort of new state. So you're basically storing sequences on a database. Each sequence is they're denoted with the letter E, and you have a database D of those sequences. Now, in terms of the Q function, the parameterization is as follows. You take a video, you use some function, pre-processing function phi, that generates a set of images. And in particular, they use 4 frames. You could use a different number depending on the game. And then you use a ConvNet, which Kwok will tell you about later today, which is sort of a cool neural network. And then there is a Q value at the output for each possible discrete action. So this is Q of A1, S, Q of A2, S, and so on. And that's the algorithm. So basically, it iterates as follows. For every sort of episode or trial of the algorithm, you start at some initial state. So you take the image, you pre-process it, and then something I haven't told you about yet, Q-learning is an off-policy method. So you are learning a Q function that allows you to choose the best action. But when you're learning that Q function, you don't need to use that Q function to take actions. You could use a different policy to take actions. These guys chose to use one of the simplest strategies in the world, which is epsilon greedy. I don't necessarily recommend it. I would rather recommend you do Bayesian optimization as an exploitation strategy. But the idea of epsilon greedy is to, with probability epsilon, you explore. You pick any action. And with probability 1 minus epsilon, you maximize the Q. You choose the action that maximizes your current estimate of the Q function. And then basically, once you have an action, you basically move the joystick. You move to the next stage of the game. You see what happens. There's a new state. And then you take this state and you store it in your database. And in order to do the backups, the gradient descent steps, what you do is you go back to your database, you retrieve these memories, and you update it based on these memories. And that's it. how to do this well is kind of what I think is really important. I'd love to understand better how to design very good databases where you could sort of plan and do counterfactuals and so on. And finally, another thing that's interesting that you can do here, an important thing that they did, they somewhat cheated because Atari is nice because there's a number on top that's, as you play, that's basically telling you this is how well you're doing. But in life, as we go about life, we don't have someone at every second telling us how well we're doing or how poorly we're doing, unless we're in a really messed up relationship. But there is another thing that really helps us going through life in a positive way, which is imitation learning. The other day I was in Edinburgh and I was walking down the corridor. I was staying at the hotel there. I went to examine a thesis, took my daughter. She's like 1.5. She just learned to walk. And I was sort of walking down the corridor thinking, a very long corridor in this hotel. And then I looked back and she can hardly walk. And she also had her hands like this. So very cute, big belly. And so children imitate and learn by imitation. And like in this cute little picture here that I got from Google Images. And so you can do the same thing. You can actually let humans play the game and straight learn a policy. Now, once you have a policy, it's possible. I'm not going to go into that. That's another lecture. But once you have a policy, you can actually now try to learn a reward function. So this is called inverse RL. So given you take an expert, you learn a policy, you fit the neural network straight to the data. And some of my students have done that. And these are the kind of filters that they get and so on. And then you try to learn a reward function, and then you play according to that reward function. So the idea is you first learn by imitating, you infer this reward function, and then you act upon the world. And as you go, occasionally you do get a new reward, and you have to update that reward function in a smart way. And I think being Bayesian about it is probably the right way to go. Finally, which one is human, which one is machine? Oh, basically, this is a chicken and it's trying to cross the road. If you haven't seen this, I just realized there's a generation gap here. I used to play this as a kid all the time. And on the left there, you can see there's a score. So right now, they're level 2-2. Three. This is probably more interesting than the Brazil-Germany. Yeah, this is kind of like that. This is like Brazil, slowly. This is Germany going straight for the goal. Look, that's totally a German goal there. 7-5. Another one. And then occasionally bump. Yeah, not. Okay, so which one is human, which one is machine? How many people think this is the human? How many people think this is the human? All right, Liz. They're both machine. Just the machine learned from different experts, thereby passing the Turing test. All right, thank you. Enjoy your lunch.